Okay, it is 1 o'clock according to my watch. I guess this one's a little bit slow. We've got all our committee members here, so that's important. And it's great to see good turnout for this Ph.D. defense colloquium. So welcome everybody. So it's my pleasure to introduce Jerrold Acdan. He's going to be talking about wildfire smoke impacts on air quality and ozone production chemistry in the Lake Michigan region. Jerrold came to Madison and joined my group in September of 2019, just a bit before the world fell apart and we all entered COVID. Before he started at UW-Madison, he got his BA in chemistry and also Earth System Science from UC Berkeley. Between his BA and starting graduate school, he actually worked for NASA, the NASA Develop program, which is an educational program run out of NASA Ames. He started out as a earth science and remote sensing researcher as part of Develop, and eventually became a project coordination fellow. And I will tell you that his organizational skills and his work ethic, I think, is reflected well in the time that he spent at Develop. Because I told his parents when they were here for graduation that normally Jerrold keeps me organized better than I do myself. During his tenure here at Wisconsin, he received a Future Investigators in the NASA Earth and Space Science Technology, or FINESS program, that funded his research here. He also spent 2 months doing research within the Atmospheric Chemistry Observations and Modeling, or ACOM, division at NCAR, working with Gabby Pfister, who has been a key part of a lot of the modeling work that Jerrold has developed. He was also a Ralph Cicerone visitor at the NCAR ACOM laboratory, again working with Gabby Pfister. So with that, I will let Jerrold take it away and he'll talk about his PhD research.
All right. Can everyone hear me fine? Great. So thanks, Brad, for that great introduction. I'm gonna today talk about some highlights from my dissertation research. But first, I want to start off by saying that air quality is a public health concern because exposure to air pollution can cause acute respiratory problems like coughing, or can worsen chronic respiratory conditions like asthma. It's also linked to premature death from respiratory and cardiovascular disease. And some air pollutants also damage plants. It can lead to agricultural crop failure. So because of these negative impacts, the United States Environmental Protection Agency, or the EPA, is tasked with enforcing the Clean Air Act in order to try to mitigate these problems. And by enforcing the Clean Air Act, they set national ambient air quality standards, or NAAQS, for 6 criteria air pollutants. 2 of those are ozone and fine particulate matter. I'll talk more about those in the next slide, but those are the 2 pollutants that I primarily focused on in my research. And then the US EPA also designates any regions that exceed these standards as non-attainment areas. And these non-attainment areas are required by law to develop plans to address the problem. All right, so diving more into the pollutants that I'm interested in. So ozone, or O3, is a gaseous secondary pollutant formed in a complex series of photochemical reactions involving precursor species called nitrogen oxides, or NOx, and volatile organic compounds, or VOCs. Around the world, but also particularly in the Lake Michigan region, NOx sources include primarily fossil fuel combustion emissions from things like cars, trucks, and power plants. And then VOC sources are both human and natural. So human sources include industrial solvents, household products like paint or aerosol sprays. And then the natural VOCs come from plants, usually. So in the Lake Michigan region, as you can see in the spot in the right, there are serious ozone non-attainment areas in the states of Wisconsin, Illinois, Indiana, and Michigan, and they all line the coast of the lake. So fine particulate matter, or PM2.5 on the other hand, are solid and liquid particles suspended in the air with diameters that are generally 2.5 microns or smaller. And unlike ozone, PM2.5 has primary emissions, meaning they're directly emitted into the atmosphere, but it can also be formed secondarily through chemical reactions. And some sources of PM2.5 include vehicle exhaust, industrial processes, residential heating, road dust, fires. Currently, there are actually no PM2.5 non-attainment areas in the Lake Michigan region. So because of this, all these complex things that I just talked about regarding air pollution formation and its transport too, the air quality research community takes this integrated assessment approach to conduct its studies. So there's a wide variety of observations that we take, from ground monitors measuring air pollution on the surface where we're exposed to it. We can take aircraft measurements, seeing what air pollution looks like at different levels in the atmosphere. There are satellite observations that provide global views of what air pollution looks like within an atmospheric column. And then my primary tool is air quality modeling. And that's using computer simulations to understand what leads to certain air pollution events, and it simulates the formation and transport of air pollution in the atmosphere while also simulating the weather that transports air pollution. Finally, there are also laboratory studies that tell us which chemical reactions are important in the atmosphere for air quality. And oftentimes, all these things combine during field campaigns, which are intensive periods of observation in which a lot of great science comes out of. So in the summer of 2023, the air quality community set off and conducted a whole bunch of field campaigns, collectively known as AGIS+. And I was a part of particularly 2 of the field campaigns at AGIS+, the NOAA Aroma field campaign, which is the A in AGIS, and then the NASA STATS field campaign, which is the S in AGIS. And for these field campaigns, the research topics included urban air quality, as well as validating the TEMPO satellite, which was just recently launched in 2023. The urban study areas included Los Angeles, New York, Chicago, Toronto, and there were observations made from aircraft and ground sites, as well as being in situ and remote sensing observations. Coincidentally, during these field campaigns, an unprecedented 2023 Canadian wildfire season occurred. And by the end of 2023, 6,000 fires had burned 15 million hectares of land, which is more than double the previous record set. And according to the Government of Canada, climate change contributed to record high temperatures and dry conditions, which provided the conditions necessary for these wildfires to occur. And as a result of these fires, wildfire smoke crossed the international boundaries, which led to degradations of air quality in the United States. Okay, so how does wildfire actually impact air quality? Well, wildfires, when they're happening, when they're combusting materials, it releases a bunch of chemicals into the atmosphere. Some of these chemicals, like here on the left-hand side, contribute to climate change because they're greenhouse gases, while other ones degrade air quality. So these ones in the middle here are actually air pollutants themselves, but also they're precursors to ozone and PM2.5 formation. And then, as well as fires directly emit particulate matter, which is also degrading air quality. So, with all of that in mind, what is the motivation for my research? I have one general guiding question, which is what were the impacts of these fires on air quality in the Lake Michigan region during the AGIS+ field campaign period? And my general approach is I'm going to use that integrated assessment approach that I discussed, using primarily air quality modeling as my main tool, but I also use ground monitor data, satellite observations, and field campaign data as well. And then the outline for the rest of this talk, so the 3 research chapters in my dissertation. Part 1, I'm going to talk about my experience forecasting for the AGIS+ field campaigns. In part 2, I'm going to talk about some retrospective modeling studies I conducted to better quantify the impacts of the wildfires on surface air quality in the Lake Michigan region. And then on part 3, I'm going to talk more specifically about the influence of wildfire smoke on the characteristics of ozone production. So that one's a little more technical. All right, so diving into part 1. So the Pierce Research Group, which I'm a part of, was part of the chemical forecasting team for AGIS Plus. And my biggest contribution to the forecasting team was I stood up 2 real-time air quality modeling forecasting systems using WRF-Chem, centered on Chicago and New York. So here you can see example forecasts for the Chicago domain, the New York domain here. Additionally, we were in the field during the field campaign to provide in-person support for flight planning activities. You can see us in the field with some people from SSCC. I got to fly on one of the airplanes for one of the research flights, which was pretty cool. It was the first time I ever been in New York, even though I wasn't in New York, I was a bonus. Yeah, so basically the usefulness of forecasting is we can tell, we can suggest to the science team while we're in the field where we think they should fly in order to measure the interesting things that we might be able to see in the field during the field campaign. So this is for the modelers out there, but if you're wondering how the forecasting system worked, they were 72-hour forecasts run daily. Again, it's a set 2 domains centered on Chicago and New York. The horizontal resolution was 4 kilometers by 4 kilometers. We had 34 vertical levels from the surface, 200 hectopascals. For meteorological initial and boundary conditions, we used GFS at 0.5 degree by 0.5 degree. And then we had chemical boundary conditions provided by global models. These included WACOM for the first part. WACOM forecasts are run at NCAR, and then BRACOM forecast, another global model, is maintained by the Pierce Research Group. I'll leave the rest for you to read, but one thing I wanted to note is that within the domain, our forecasting domains themselves, like these domains, I did not include fire emissions, and that's because it's hard to get fire emissions that are in forecasting mode, like looking into the future. But also, a majority of the Canadian wildfires that occurred were outside of the modeling domain anyway, so therefore any smoke impacts are actually entering through the boundaries. I also want to say thank you to the people who maintain the S4 supercomputer at SSCC, because that's where the forecasts were run. Okay, so as well, during the field campaign, there was an observational super site set up in Chewauquee Prairie, Wisconsin. So what Chewauquee Prairie here, denoted on this screenshot of Google Maps, is a rural area downwind of Chicago. So if the wind's going this way, it's downwind of Chicago along the coastline. And it often experiences high air pollution because of the transport of pollution from this general area northward. The Wisconsin Department of Natural Resources keeps a routine air quality and meteorological monitoring data there. So there's ground instruments there measuring air quality and like winds and things. Also during the AGIS Plus field campaign, Professor Mike Newchurch's group from the University of Alabama in Huntsville was there to collect more observations. They had a mobile laboratory called the Rocket, which hosts a differential absorption LiDAR, or the dial, and that provides vertical profiles of ozone and aerosols, which is a very useful data set to see how air pollution looks vertically. And then also, Professor Newchurch flew this plane called the Sea-Ray, which measured, again, in situ air quality and meteorological data, particularly over the surface of the lake, which is also important to air pollution transport and chemistry in the region. So part 1 of this research, what am I asking and what are my methods? I am interested in knowing what was the forecast skill at Chewauquee Prairie and how does it vary with lead time and altitude. And I'm going to answer this question by evaluating the forecast using rocket vertical ozone profiles measured from that mobile laboratory, as well as the surface measurements from the DNR. And then overall, I want to know what insights can I gain from these evaluations that can inform improvements to the WRF-PEM configuration for retrospective modeling studies, which I did later for parts 2 and 3 of my dissertation. Okay, so I'm going to start the forecast evaluations by looking at a specific case study date. So this date is July 25th, 2023. And on the left are plots of ozone air quality index values, and on the right is for PM2.5. We can see that any colors that are orange or lower here or here are considered to be exceeding federal regulatory standards. And as you can see for both pollutants, that there's widespread exceedances all around, particularly along the coast for ozone, but also spread out throughout the domain for PM2.5. In Chilwaukee Prairie that day, it was the highest ozone value measured all year. For PM2.5, it was the fourth highest value measured the whole year. All right, so how did our forecast look from a vertical perspective? So I mentioned earlier the rocket LiDAR. So this is the mobile laboratory that hosts the LiDAR, and this is the kind of data that it produces. So over time, it's looking upward into the atmosphere and measuring ozone at different levels. And you can see how the air looks like as time goes on. And then here's the day 1 forecast, the day 2 forecast on July 25th, and the day 3 forecast. And when I say day 1, 2, and 3 forecasts, what I mean is that the day 1 forecast was initialized on the day that we're analyzing. The day 2 forecast was initialized on the day before the day we're analyzing, and the day 3 was 2 days before. So in a sense, the day 3 forecast is looking the most into the future. So as you can see in the observations, we have pretty high ozone levels, around greater than 80 in the earlier part of this period. And then towards the end of the day, we can see that the values increase to almost greater than 140 parts per billion, which is very, very high. And then we can compare that to how the forecast did. You can see that the day 1 and the day 2 forecast kind of model this plume decently well, though the timing and the magnitude are kind of off. And the day 3 forecast, which was looking most in the future, doesn't really capture this plume around 1 to 2 kilometers above the surface. Here are some statistics for below 2 kilometers, which is where this big plume exists. We can see that they're all biased low, but the day 1 forecast has the best correlation, which we kind of expect because it's looking less in the future than the other forecasts. Okay, how did it look from the surface now, not just from the vertical perspective? On the top, we have surface ozone, and then on the bottom, we have surface PM2.5. The observations are in black, and then the day 1 forecast is in this pinkish color, the day 2 forecast in this blue color, and the day 3 forecast in this yellow color. And then this dashed line represents the regulatory level at which, if it's above, it's generally exceeding the regulatory levels. So as we can see in the observations and in the models and the forecasts, that in the early morning towards the midday that the values increase in ozone, but for the observations they remain high above 100 towards the end of the day, but all the forecasts start declining in ozone. So essentially the forecasts don't maintain this high ozone plateau after 19 UTC. And then for surface PM2.5, we can see that all forecasts are very, very low compared to the observations by factors of almost greater than 4 throughout the entire day. So the question is, why, right? Like why are we so low in PM2.5? And what are some possible reasons for the discrepancy in ozone as well at these high levels? Well, as you probably might have guessed, by the title of my dissertation, right, wildfires played a big influence in what happened this day. So on the left are NOAA high-split map trajectories. So the NOAA high-split model allows you to run map trajectories starting from a location. So this one here is starting from Chilwaukee Prairie, the place that I'm analyzing. And it allows you to go back in time to see where the air mass came from that eventually reached Chilwaukee Prairie. Here, the colors don't represent the forecast. These are just different starting altitudes, so I'm sorry that I use the same colors, so don't get them mixed up. And then on the bottom here, you can see the altitude of the trajectories as they travel through time. So like I said, they start here at the star and then move backwards. And on this plot, the star starts on the left and then moves backward this way, just for reference. So what do we see about this air mass? Well, I'm going to go forward in time now rather than backwards, just for easier explanation. We can see that the air masses are coming from Canada, and they eventually flow over Minnesota, through Wisconsin, and then circle around the Chicago metropolitan area here before being pushed over the lake and then pushed back onshore at Chewacla Prairie. And here on the right side is true color imagery and aerosol optical depth imagery from the GOES-16 satellite. Aerosol optical depth is an indicator of wildfire smoke within the atmospheric column. It measures how much particles are reflecting the sunlight away. And as we can see, over the time periods that are similarly noted on this back trajectory, that it perfectly follows the high AOD that we're seeing in this image. The purple colors are higher AOD. We therefore can infer that, yes, these air masses were mixing in with wildfire smoke and impacting the air pollution levels that was eventually measured in Chewacla Prairie. All right, what's another thing that can be learned from this case study day? Well, another thing that I wanted to look at was the impact of the number of WRF model vertical levels that we had in our configuration. So in our forecast configuration, we had these levels here in red. And then on this plot is nitrogen dioxide, or NO2, plotted versus altitude, measured from the Sea Ray aircraft by Professor Mike Newchurch, particularly when he flew over the surface of Lake Michigan. And one thing we see is that a majority of the observed variability in NO2 over the surface of the lake actually occurs below 250 meters altitude, which is very low over the surface. And our forecasting configuration, that only covers about 2 model levels. So our forecast didn't necessarily capture this variability very well because all the data lies only in 2 levels. Therefore, if we included more model vertical levels, we'd probably better capture this variability. And in the retrospective simulations I conducted later, I did increase the number of vertical levels. As you can see now, the new levels, this variability spans about 4 to 5 levels, which is better for simulation. Okay, so now that I talked about the now that I talked about the case study day, how did the forecast system look overall days during the field campaign? Here again, I'm using the rocket data, which are the vertical profiles of ozone. On the left is the mean ozone profile across all days of the field campaign period. Again, the observations are in black, and then the forecasts are in the same colors that I mentioned earlier. In this plot, these horizontal bars are the mean observational uncertainty in each altitude bin. And then the middle is the root mean squared error calculated by comparing the observations to the forecast and the correlation coefficient. So what do I find? I find that from 0 to 4 kilometers, the day 1 forecasts have improved mean, or closer to the mean, have lower root mean squared error values, and also higher correlation coefficients than the day 2 and day 3 forecasts. So essentially, forecast skill degrades with increasing lead time, which is kind of as expected. And then one thing I also wanted to highlight was that from 0 to 2 kilometers, which is the layer that's most important for air quality, the day 1 and 2 forecasts have skill, it's noted by the correlation coefficient greater than 0.6. Above 4 kilometers, the results are a little more mixed. Okay, so part 1 of my dissertation, this is the summary of what I just talked about. So the first research question, how does ozone forecast skill at Chewacla Prairie vary with lead time and altitude? Below 4 kilometers, the forecast skill degrades with increasing lead time. In other words, the day 1 forecast is the best, and the day 2 forecast is the worst. below 2 kilometers, the most important layer for air quality, the day 1 and 2 forecasts have skill. And then what insights do I gain from these evaluations? The biggest one is that for a retrospective simulation, I will need more accurate fire emissions in the chemical boundary conditions in order to better capture the impacts of the Canadian wildfire smoke. And then also increasing the number of more model vertical levels, particularly below 2 kilometers, would help capture the vertical variability of chemical species, particularly over the surface of Lake Michigan. All right. So moving on to part 2. So now that I've talked about forecasting and evaluating these forecasts, that big question is, what were the impacts of the Canadian wildfire smoke on surface ozone and surface PM2.5 air quality levels during Aegis Plus in the Lake Michigan region? And then later on, I'm also going to ask, did the aerosol shading effect on ozone production occur? I'll talk more about that right before I talk about the results for that. So how I conducted my methodology to answer these questions is I conducted 3 retrospective WRF-Chem experiments using Wacom chemical boundary conditions with differently scaled Canadian wildfire emissions. So for the rest of this presentation, these model labels refer to the 3 different experiments I ran. So the CFX0 experiment is one in which I set the Canadian fire emissions to 0 within the boundary conditions. This is a what-if modeling scenario that tells us what air quality would have been like without the fires happening. The CFXR experiment is one in which I scaled the fire emissions by physiographic region within Wacom. I'll talk more about that later. And then the CFX5 experiment, I multiplied the fire emissions by 5 within Wacom. And then in order to evaluate the impacts of these fires, I'm going to look at differences between these WRF-Chem experiments, particularly the ones with wildfire minus the ones without wildfire, just to see what the air quality levels difference between the models look like. And then I'm going to also compare these to observations. Particularly, I'm going to compare these to ground monitor data from the US EPA Air Quality System database, as well as, again, satellite data from GO16 for aerosol optical depth. Okay, here's, again, for the modelers, the retrospective configuration highlighted in red are the things that changed between when, what I used for forecasting versus what I used for these retrospective simulations. So here I increased the number of vertical levels, as I said earlier, with more levels below 2 kilometers. For meteorological initial boundary conditions, I decided to use the model, which is much higher resolution than the GFS data that we used before. Again, for chemical boundary conditions, we're using 3 different Wacom simulations with differently scaled Canadian wildfire emissions. I'll talk more about that later, but within these Wacom simulations, for the fire emissions, they're calculated by using Q-fed fire detections with fin emission ratios applied. Other aspects, I did include fire emissions this time within the modeling domain, but note a majority that of the Canadian wildfires occurred outside the domain. So again, the smoke impacts are through the boundaries primarily. I also turned on the aerosol radiative feedback, so differences between the simulations are due to the emissions from the wildfires, but also how those particles interact with the weather, things like that. Okay, so I mentioned earlier that I have a set of different Wacom chemical boundary conditions, and the reason why we have so many different kinds of Wacom boundary conditions was because I originally ran Wacom using a Q-fed fin fire emissions as originally acquired, and when I compared the results to surface PM2.5 levels to observations, there were large underestimates in the simulations. So I decided, to get better representations of what actually occurred because of the wildfires, I tested other simulations where I scaled the emissions by 0, 2, and 5. And I actually found that through comparisons with observations that depending on where the fire emissions were released, the better performance depended on the scaling factor that I chose. And I noticed that they kind of lined up with these physiographic regions. And so what I decided to do is to combine the different scaling factors for different regions. And you can see which scaling factor I applied to each region here. And so this regionally scaled vacuum simulation is what I used for the boundary conditions for my CFXR experiment. The one where I used 0 as the scaling factor within the Canadian emissions is the CFX01 and then the 5 for the 5. Okay, so now how did the model do over the entire period? Here's just a video loop showing surface ozone on the case study day that I talked about, July 25th during forecasting, just so you can see kind of what the differences look like between the model simulations. I'll run it again. So on the left is the experiment without Canadian wildfires, and the right is the regionally scaled Canadian wildfires, and then in the middle is the 5X wildfires. It's kind of fun to watch, in my opinion. And then here are some statistics evaluating how the models did compared to data from 73 ozone ground monitors during the entire 25-day study period, so not just on the case study day. Yeah, the statistics I'm providing are normalized mean bias, so how biased are observations and correlation coefficient. The experiment without wildfires was biased low, which tells us that that wildfires actually increased ozone levels during this period. The regionally scaled did the best, and the 5X experiment is actually biased a little high. All do pretty well with terms of correlation. Okay, similar thing for surface PM2.5. You can see very large differences between the models. In terms of statistics, without including the Canadian wildfires, we can see that the normalized mean bias is negative 57.1%, was really, really biased low, and that it's not correlated really at all with observations. The regionally scaled and the 5X do a little better. The regionally scaled is still biased low, and the 5X is actually biased a little high, but their correlations match much better, greater than 0.6. So that tells us that during this period that the Canadian wildfire smoke is actually can explain a lot of the variation, the temporal variation in PM2.5 levels in the region. Here's the same thing for aerosol optical depth. So now this is not just at the surface, but also how much wildfire smoke is it within the atmospheric columns. So we can see here that compared to satellite data, that all three simulations are biased very, very low. It gets a little better as you include more fire emissions. However, similar to PM2.5, we can see that the correlation improves when we include wildfires. So again, that tells us that aerosol optical depth, a lot of its variation can be explained by the wildfire smoke. So why are the biases so large? Well, within WACOM, which provided the boundary condition, the chemical boundary conditions, there's no fire plume rise. Fire plume rise, when wildfire smoke is being emitted, it can travel higher to the atmosphere before being transported horizontally. But within WACOM, it's actually all released from the surface. So maybe that explains why there's not enough wildfire smoke higher up. As well as the go-kart aerosol model, which is used to simulate aerosol processes in this model. Within the WRF-Chem simulations, it doesn't include all types of PM2.5. And it also doesn't simulate secondary formation, so there's going to be underestimates because of that. Okay, so now that you know how the models generally did, I'm going to use time series analysis to identify periods of wildfire influence. So here on the top row are the mean ozone across all monitor locations, mean PM2.5, and mean aerosol optical depth. I'm mostly going to focus on these two, but here you can see how we're underestimating AOD by a lot. generally follows the same patterns that the increases in PM2.5. Okay, so I want to highlight 4 periods with varied impacts of surface, various impacts of wildfires on surface ozone and PM2.5. So during this first period, from July 23rd to 25th, we see the largest impacts of wildfire on ozone and PM2.5. And I'm determining this by looking at the differences between the simulations without wildfires and with wildfires. You can see here, there's pretty big differences. On the second period, PM2.5 levels are actually pretty low compared to the first period. And the differences between the simulations are smaller than the first period. Same thing for ozone. And actually during this period, there were ozone levels exceeding the federal regulatory standards around the Lake Michigan region. And because there are, very small differences between the simulations, it's likely that those ozone exceedances probably would have occurred without wildfire smoke. And then in these third and fourth periods, we do see wildfire influence on PM2.5. Again, differences between the no wildfires and wildfires. However, I don't necessarily say that there's an influence on ozone because actually our model simulations overpredict ozone in these 2 periods. So we do see like the impact of smoke within the models, but like because we're overestimating, I can't say that it's actually happening. Yeah, so there were varied impacts throughout the time period. It didn't happen all the time. Okay, so another question that I wanted to ask in this chapter of my research is, did the aerosol shading effect on ozone production occur? So in addition to increasing degrading air quality, wildfire smoke actually has a secondary impact that can occur. So when there's a wildfire plume wafted higher into the atmosphere, the particles within the plume can actually scatter or absorb incoming sunlight, and that reduces the amount of shortwave radiation reaching the surface below the wildfire plume. And so that leaves less sunlight for photochemical reactions that can occur below the plume. And a lot of photochemical reactions that are important to ozone production need sunlight. And therefore, because of this reduction in incoming sunlight, that leads to less ozone production near the surface, which is an interesting secondary effect. And so I wanted to know, can I see this happening within my model simulations? Okay, so to explore this impact, what I did was look at the difference between the CFX5 experiment and the X0 experiment without wildfires. I'm comparing the 5 to the 0 because the 5X experiment simulated aerosol optical depth better than the other ones. And here in this plot on the left, I'm looking at the change in surface PM2.5 at AQS groundwater locations within the simulations versus the change in ozone. And one thing that I noticed visually is that at the highest PM2.5 enhancements, so probably like greater than 40, that there are 2 branches in the ozone enhancements. You can see that the ozone enhancements are higher in this branch than this branch, even though they're at similar PM2.5 enhancements. So I wanted to analyze in more detail these 2 groups, but to better define them, I applied a k-means cluster group algorithm to better identify them. And from that algorithm, I identified cluster 4 as this upper branch and cluster 5 as this lower branch. So after identifying the branches, I decided to look at the median values of various aspects related to the aerosol shading effect on ozone production. As we can see here, C4, the upper branch, has lower AOD, and the upper branch has lower AOD, but the lower branch has higher AOD. We also see in this lower branch that the reduction of downwelling shortwave radiation is even higher. And also the photolysis reactions that I talked about previously are also decreased even more in this branch. So to me, this shows evidence that yes, the aerosol shading effect did occur, because even though surface PM2.5 enhancements are similar in this side of the figure, there are differences in aerosol optical depth that lead down this chain of shading and decreased ozone enhancements. I do note that within these two branches, it's only 4% of the data that's included in all these points, but we are interested as the air quality community in what happens at the very high levels. So, even though these are a small number of points, they are important to air quality. Okay, so part two, what did I just talk about? What were the impacts of the wildfire smoke on air quality levels? Our simulations show that there are general regional enhancements of surface ozone, surface PM2.5 and AOD to the wildfire smoke, but those wildfire influences varied throughout the period, so it wasn't constant throughout. Second, did the aerosol shading effect occur? Yes, there appears to be two branches in ozone enhancements when the PM2.5 enhancements are greater than 40 micrograms per cubic meter. And just as I explained, there's higher aerosol optical depth, which leads to shading and ultimately diminishes the amount of ozone that's produced. I do want to note that I showed that our experiments underestimated aerosol optical depth by a lot. And so that kind of suggests that the aerosol shading effect probably occurred more often than was modeled by our simulations. Okay, part three. So after talking about how the wildfires influenced surface air quality levels, now I'm going to dive more into how the wildfires possibly influence the characteristics of ozone production. And then I'm also interested in knowing were the elevated concentrations of ozone that were observed during Aegis Plus a result of ozone production within the Lake Michigan region itself? Or did that production occur further upwind, like when the air was still in Canada, for example? So to do this, I'm analyzing different outputs from the WRF-Chem simulations. These outputs are integrated reaction rates, or IRR, and these are individual gas phase reaction rates that allows for the exploration of the chemical transformations that are described in the chemical mechanism that I use. And then I also use trace gas tendencies, which are changes in a species concentration before and after model processes such as due to chemistry or advection. And I'm going to analyze these questions from a Eulerian or local perspective, so what's happening locally, versus a Lagrangian following transport perspective, so what's happening as an air mass is moving. Really quickly, I'm just going to drink water. Okay, so when I'm talking about the characteristics of ozone production, what am I referring to? I'm going to talk about three of them, but as a reminder, ozone production is a complicated nonlinear chain of photochemical reactions involving VOCs and NOx. Here's like a simple diagram of an ozone production mechanism here. And so one of the characteristics of ozone production is VOC reactivity. It's a measure of how much VOCs, shown here, are reacting with this species called OH, thus contributing to the ozone production chain. And that can be calculated with the IRR output that I talked about earlier. I can also use IRR output to identify which VOCs are the ones contributing the most to ozone production. Okay, so this one's a lot. But the second characteristic of ozone production is its sensitivity to its precursors, NOx versus VOC. So here is a diagram called an ozone isopleth. On the x-axis are VOC concentrations. On the y-axis are NOx concentrations. And then in the color, it shows how much ozone is produced at different concentrations. And general ozone production is highest here, and it's lower around here. So we can categorize ozone production as VOC sensitive when NOx and VOCs are in this general region, So when NOx is high and VOCs are low, and we say it's VOC sensitive because if we increase the amount of VOCs, we increase ozone production, and then we decrease this way. Similarly here, the NOx sensitive regime is when VOCs are high and NOx is low. If we increase NOx in this regime, we increase ozone production versus decreasing. So knowing the ozone production, like which regime it's in, is important for air quality managers because they can know which kind of emissions to target, for example. Like, should we reduce VOCs more or NOx more, things like that. So it's pretty hard to identify which regime you're in. It requires often detailed chemical modeling like I did. But one way to identify the regime is through how this whole cycle terminates. And the ozone production cycle terminates when these species called hawks are removed from the system. And when hawks plus hawks, so when these species reacts with themselves, that's characteristic of the NOx sensitive regime. This is called LROX. And then when hawks reacts with NOx and terminates the chain production that way, that's characteristic of the VOC sensitive regime. So this process is called LNOx. And we can use the relative ratio of them to determine which regime we're in. A study found that when the ratio of LROX to LNOx is about 0.35, that's the transition point between VOC and NOx sensitivity. And I can use the WRF-Chem output from IRR to calculate LROX and LNOx, and therefore identify which regime the chemical production is. That was a long one. Sorry for that. And then the last aspect that I'm going to analyze is the net chemical production. So here, how much ozone is actually produced in the end. So the net chemical production is just the sum of how much ozone is produced through chemical reactions versus how much is lost, subtracting how much is lost. And that can be analyzed with the trace gas tendency output I talked about earlier. Okay, so I first conducted these analyses Eulerian, looking locally in different regions around the Lake Michigan region. And what I did was, looking at the different characteristics I just talked about, I created mean diurnal plots over the 3 days of the largest smoke impacts. So that was July 23rd to 25th. And for brevity, I'm only going to show you two of the results for two of these regions. For Chicago, this box here, and then over the surface of Lake Michigan, this box here. On the top, this is just for reference, this is what ozone looked like across the modeling simulations. And then the characteristic of ozone production that I'm focusing on is here, which is for the first line VOC reactivity. So what do I notice? VOC reactivity is highest in all simulations in the middle of the day, and that the wildfire smoke, so the simulations, there's the key again, with wildfire smoke, shows that the VOC reactivity actually increases midday due to VOCs that are present within the wildfire smoke. I also found that carbon monoxide, CO, is actually the most reactive VOC in all simulations, so with and without wildfire smoke, but that its reactivity is 2 times more in the simulation with the most wildfire smoke. Okay, how does the production sensitivity look over these two regions? So again, the ozone is just plotted there for for context. But here, again, these are the ratios of LROX to LNOx, which can be used to identify which regime the ozone production is. You can see that throughout the day, the regime changes. In the morning hours and in the night hours, ozone production is VOC sensitive. But as the day goes on, during the midday, it goes towards NOx sensitivity, both over the water and over the land. And we can see that actually wildfire smoke does change the regime that we're in. So particularly at the peak hours in the afternoon, we see that in the no wildfire smoke simulation, the regime is transitional, but in the other ones, the regime is NOx sensitive. So overall, wildfire smoke shifts ozone production to be more NOx sensitive. Okay, so now looking at net chemical production, this is the diurnal cycle of what ozone production looks like. When the value of net chemical production is negative, that means ozone is actually being destroyed over a region, versus when it's positive, it means it's being created. We can see that over land, that during the nighttime and during the morning and nighttime hours, and that ozone production is actually negative. So more ozone is destroyed, and it's only during a small window over Chicago that ozone is actually produced. Over the lake, the values are generally more positive, so that means more ozone production is occurring over the lake. When I integrate these values, so when I sum the values over this entire period, that can tell me whether throughout the day whether ozone is created or destroyed. As we can see for Chicago, the daily integrated net chemical ozone production is actually negative, so that means more ozone is destroyed over land in Chicago than is created. And we also see that actually the experiment without wildfires, that it has less destruction than the experiment with wildfires, which is a very interesting finding because we would expect that wildfires would increase ozone production. Similarly, over the water, here the net ozone production is positive over the water, but the wildfire simulation, or the simulation without wildfires actually has slightly more ozone production. Again, showing that including wildfires has slightly less ozone production, which is also an interesting finding, though the values are closer here. Okay, so that was from a local perspective. What does it look like following transport? So here again is another NOAA high-split back trajectory run through the model simulations. Just as before, the location of the back trajectory originates where the star, this time I chose the back trajectory starting from a place in Chicago, which is in that region I showed earlier, in the middle here. Again, following back in time, going this way, the star is where it locates. This is where it's shown here in the altitude plot of the trajectories. And then in these plots, which show the wharf chem output sampled along the trajectory, again, the star here, so this is its original location, and going backwards in time this way. So looking at the different characteristics of ozone production that I just went through earlier, what does it look like along this trajectory? Well, for ozone concentration specifically, we can see that the largest differences are actually at the model boundary. When the air mass enters the domain. At the end, the wildfire experiment, CFX5, still has the highest values, but they're much closer now than when they started in the boundary. VOC reactivity, as shown before, wildfire smoke leads to periods where VOC reactivity slightly increased during the daytime, particularly when the trajectory is within the boundary layer. For ozone production sensitivity to precursors, again, we can see in the wildfire experiments that that ratio LROX to LNOx is increased usually compared to without wildfires. But here this time we don't see a major, like a classification difference between the different experiments. And then again, the big finding to me is the net chemical production. When we integrate over this full trajectory, we find that net ozone production is actually higher in the experiment without. Sorry, this value shouldn't say 39, it should say 30. But anyway, it's highest in the experiment without wildfires compared to the ones with wildfires. All right, so what did I find here? I found that wildfire increases VOC reactivity during the midday hours, and that carbon monoxide is the most reactive, and that its reactivity is higher when there's wildfire present. I also found that the wildfire smoke shifts the ozone production regime towards NOx sensitivity. And then in terms of, did the elevated concentrations of ozone that were observed result of ozone production within the region, or did it occur further upwind. We saw that net ozone production within the modeling domain was actually higher in the experiment without wildfires compared to the ones with. Yet the actual ozone concentrations were higher in the wildfire experiments, so that tells us that wildfire enhanced ozone production occurred further upwind in Canada. Oh, another error, sorry, A. But yeah, so it didn't actually occur within the domain in our modeling simulations, which is a big question that people had. Was the ozone created before it entered our region, or did it happen within the region? And my research shows that it likely happened earlier when it was in Canada. So these are the conclusions. I'm not going to go over them because I'm running out of time, but yeah, they're here. I just want to also highlight that air quality and climate change are inextricably linked. Here's a study that tells us that the frequency of boreal forest fires, such as the ones that happened in Canada, are projected to increase in the future. If you look here, this is the future end of 21st century minus present number of years, with at least 1 month classified as fire prone per decade. It's greater than 4, which means every other year we might expect major wildfires to happen in Canada by the end of the century. And therefore we should expect air quality degradations to continue to occur due to wildfire smoke to be more regular in the Lake Michigan region in the future, because climate change is happening. And it happened this year. For example, July 13th, 2025, we can see surface PM2.5 air quality levels was degraded over this region. Air sample depth showing it was likely wildfire smoke that caused this. All right, and with that, I just want to give thanks to a lot of people. I want to thank my committee members, particularly my advisor, Brad Pierce. Thank you for everything. I want to thank the Pierce Research Group for all the talking about research that made the experience more vibrant. I want to thank the Aegis Plus science team for allowing us to be a part of the field campaign, but also for creating a bunch of data sets that's useful for the entire air quality research community. I want to thank the AOSS community for making this building a vibrant place. And this research was made possible, as Brad acknowledged earlier, through my visits to NSF, NCAR, ACOM. I'm grateful to have visited them. And yeah, this research was funded by a NASA Finance grant. And I want to thank all my family, friends, near and far. I love you so much. And I'm happy to take any questions.
We've got time for a few questions. We can take questions from the general audience and save the committee questions.
Yeah, Jerry, really interesting, comprehensive, lots of cool things in here. I wish I knew more about it. But I want to ask you something about the tools that you use, the modeling tool.
Yes.
And I had to sort through a bunch of things that came to mind to me, but I'll ask you the one that stays kind of at the front. If you could loft the smoke in your model, and maybe there's a way to parameterize that, can you assume a certain buoyancy for a smoke fire or something like that? If you could loft the smoke, would that change any of the results in part 2?
Okay, so yes, you can. Actually, there is parameterizations for fire plume rise within models.
Yeah.
It just wasn't included in the Wacom global model that I used to create boundary conditions. It was included in my WRF-Chem domain, but again, most of the fires were happening outside of my modeling domain. And yes, so when I was explaining here, sorry, going back a lot. So I expect that if I were to loft some of the wildfire emissions higher in the atmosphere, that we would decrease the bias in AOD, and also backwards. Also, we were slightly over predicting in this experiment PM2.5s over the time. That could be because some of the PM2.5 wasn't being lofted higher.
Yeah, that's what I was wondering.
Yeah.
Okay.
So I'd expect maybe that would improve. But in general, the fact that I had to apply scaling factors to the fire emissions data set shows that these data sets need continual improvement and things like that.
Are there any ancillary impacts on the chemistry in part 3 that might come from that adjustment?
Yeah, for sure. So a lot of the chemicals that I scale in the fire emissions will interact with the chemical production chains and change the chemistry.
Yeah, interesting, thanks.
Yes.
Great talk, that was really interesting, Jerome. I had, I guess, a kind of similar question about, but more on your domain size. So your work from domain was 4 by 4 kilometers over the Chicago area, right? So, which left all of the fire emissions in the boundary conditions.
Basically, yes.
Would you expect, how would you expect changing it to a larger domain over more of Canada would change your results? Because I imagine you would have to use a larger resolution, and that's over the urban area, could change the...
Yeah, so I went with 4 kilometers because that's generally a good size to look at urban air quality in particular. And you know, the more grid boxes you have, so if I were to expand the domain, the more computational power it requires, and my simulations already took months to complete at a time, so it was a lot. But I would expect, you know, because when we're using chemical boundary conditions, there's an interpolation that occurs between the two, you know, at the boundary of the species, so that could lead to some errors. There are actually new models that cover the globe, but then regionally refine over specific areas, like MPAS or Musica, that are, you know, having chemistry input into them. So that might be like a, you know, a better way to conduct this kind of research in the future.
Hey, really nice job, Jerrold. Great work.
Thank you.
May not be a totally fair question, but do you know, I was really, really interested in the result that you're finding that ozone is being transported in as opposed to forming kind of in the region. Do you know what other results from AGES are finding? Like, where they actually directly measured that? Do you know if I'm trying to remember what I've heard. I don't
Yeah. As far to my knowledge, I don't think anyone is specifically looking at that. Some people are starting to look at aircraft observations and seeing if that impacted, you know, the shading effect, if that occurred. But that's a little hard because, you know, it's like what would have happened without the aerosols, but you can't do that in real life. So that's why we're using models. And I think, you know, we're at the forefront of that question. And I think, you know, the results show, at least, you know, within our model simulations, it occurred further upwind.
That's really interesting. Thanks.
Yes.
Building off the first 2 questions, it seems like all this atmospheric species would be quite affected by the boundary layer height and the boundary layer evolution each day, and the boundary layer evolution heterogeneously over this region. Are there any boundary layer depth, for example, measurements you can compare your model runs to? And if you don't have any of those or not enough good quality ones, if you just compare the 3 different sets of modeling, of hindsight modeling outputs with the different Wacom boundary conditions, how do the boundary layer depths and things compare between those 2? Because that would be another way to loft stuff or create stuff higher or lower than what you're seeing in the models right now.
Yeah, so it's a good point. There aren't too many, you know, measurements of PBL height going on. There might be a celiometer somewhere. Yeah, maybe 1 inch-watt per area. I don't know if it's working right now. There might be 1 in Chicago too. I haven't compared, you know, how well the PBL height is modeled, but I don't know if it's showing in my results, but yeah, I didn't show it here, but I only plotted one of the simulations PBL height, but I did look at them across the simulations, and they are pretty similar actually. There's slight differences because the fire emissions can impact the meteorology through the aerosol radiative feedback, but they weren't super big.
And that's the other thing is that you increase the model resolution at the surface, but what if you increase the model resolution throughout the boundary layer, as much as you could? I understand there are computational reasons. Could that increase your fidelity of the entrainment zone that may mix some of these things and allow processes to occur or not occur, depending.
Yes. Yeah, so that was what I attempted to do with the retrospective simulation, you know, put a certain number of levels that, you know, seemed reasonable computationally, but of course having as many vertical levels as we could would probably result in better simulations.
Thanks, great job.
I'll just add, in 2017, we did a Lake Michigan ozone study, and we had the Spark trailer out there, so we had area temperature and water vapor profiles and a WinPro LiDAR, and we were able to evaluate the boundary layer depth very carefully during that study. We did have a WinPro LiDAR at Chilwaukee Prairie that we could look into more.
Nice.
Okay, I guess we're, one more question?
Yeah, on slide 34, when you were showing the two different branches that you'd clustered together, I was wondering if those, so you clustered them just by these two, yeah.
Well,
Are
yeah,
those
just these data points and then these data points separately.
Yeah, are they related in time at all? Like, is this two
Yeah.
distinct events that are occurring?
So I actually did not look at that. This is just a scatter point of all the data points
Yeah.
throughout the study period. Ideally that's what would be the best to look at to see if they are related in time.
Mm-hmm.
Yeah, well actually no, sorry, they're not related in time because each data point represents a different measurement.
But those are like, this is hourly measurements over your entire.
Yes.
So I wonder if like two of those, like you had two really large events where it seemed like the wildfire smoke. So I wonder if this is like the peak of one event and then the peak of the other
Yeah.
event is like those hours put together.
That would be good to look at.
Yeah. And then that maybe the different conditions might also help you explain what's going on or give you a better sense of why that's happening. And I was also wondering whether or not that was like, if this is due to the shading effect, if that's like different times of day. That was the other thought I had, as if like during the morning and evening hours, if it like switches from one branch to the other or something.
Yeah, I mean, I did filter out after certain solar zenith angles, because
Okay.
then there wouldn't be,
There's nothing going on.
Yeah, there's nothing
Yeah,
going
yeah.
on. But, it could be a function of the hours in that
Yeah.
time period left over.
Very cool.
I don't know, do you have a quick one? Is it cool? Oh.
I was wondering if you had a deeper understanding of the cause of underestimation from the thin emissions and sort of why it was regionally distinct for the scaling factors.
Yeah, I don't know, actually. I didn't develop the emissions myself. Sometimes it could just be like, since they're, detected with satellite observations, that sometimes those fires are missed because it's, there's too much wildfire smoke or it's cloudy over the fires. It could be that the emissions ratios, don't apply the best over large regions, things like that.
Okay, thank you.
Yes.
Okay, let's give Jerrold another